Good. So let us start with trying to recall what we were doing and why. And obviously the why part is a joke. There is no real reason for doing this, except for me agreeing to deliver this course. So we consider it a stochastic differential equation. I will write everything in one-dimensional case, again, because it's easier and it looks nicer, but it all works in multi-dimensional set except for, as we talked a bit less time, except for multiple stochastic or mixed integrals. If you can calculate them in one-dimensional case, but generally speaking, if you have multiple linear processes involved, they're hard to deal. So for SD, we introduced the so-called Ito-Taylor expansion. As a rather formal series, in which sense formal? Because we didn't discuss when the series is convergent. And typically in the setting of numerical methods, the series is never considered as a whole, it's always truncated at some step. So you effectively need good behavior of the behavior of derivatives of your coefficients up to the level where truncated plus one, because you need to estimate what happens after as follows. So let us introduce two differential operators, L, for instance, 0, which is dt plus a dx plus 1/2 sigma squared dx, and L1, which is just sigma dx. Then we can iteratively use the Ito formula. Good, only Ukrainian. Psi of t is then psi 0 plus a0 psi 0 t, linear part, plus sigma 0 psi 0 wt, still linear part, plus integral from 0 to t ds integral from 0 to s dr a r psi of r, plus two iterated integrals, integral from 0 to t ds, integral from 0 to s dwr L1 from a again, plus integral from 0 to t dws, integral from 0 to s dr L0 sigma, and plus s dwr L, let me check, L1 sigma. And repeating this procedure, we formally arrive at the series of the form dw alpha 1, S1 dw alpha 2 from S1 from S2 from 0 S k minus 1 dw alpha k s k, where our alpha is alpha 1 alpha k, or the set of all such k tuples such that k belongs to n, and alpha g is from the set dw1 is just dw, dw0 is just dt, which is standard notation. And f alpha is a sum combination of derivatives and of our coefficients. And now truncated in some level, we obtain a numerical scheme. Then the remainder consists of mixed integrals of such types, and the remainder, however, include not a fixed coefficients before it, but it will contain a proper non-constant integrand. So if effectively to prove that the scheme has a specific order, we will need to estimate such integrands. And we also talked about some mnemonical rules that ordinary integral gives order 1 to our scheme if you include it. Stochastic integral gives order 1/2. This is because w squared symmetrical is just t, so formally dwt is like t1/2, which is not really true, but somewhat close to reality. It's a mean square sense. It's not really in almost surely sense. And typically by considering coefficients with bounded derivatives of necessary order, it can be possible. And because we have mixed integrals, generally speaking, we have a slightly different situation compared to the case of ordinary differential equation. We have schemes of order 1, 2, etc. Here we have schemes of order 1, 1/2, 2, 2.5 by truncating on different levels. So if we conclude just this part, we formally obviously can neglect this, This is of order second order, this is of order 1/2. 1.5 here, and this is formally of order 1 also. And still the scheme works. And by using this part or excluding it, we obtain two different schemes, effectively of order 1/2 in mean square and 1 in mean square. So it's slightly it illustrates this informal rule how you calculate the order by looking at this mixed integrals. We will, however, do it slightly differently, not in this general setting. I refer to the book of Claudin and Platen for very general discussions of such stuff. And also we restrict ourselves, as I already said, only exclusively to this one-dimensional case, because it simplifies notations and makes things easier to read, but it does work in multidimensional settings. So let's recall and investigate the Euler-Maruyama scheme. I will write EM, but not as expectation. It's the EM algorithm, but the EM scheme. So we just use the linear part of this decomposition, of this expansion, to define our scheme. So let us introduce T and K's, K divided over N, T, K ranges from 0 to N, and is the nature of positive integer. Delta N is just T divided over N is the size of partition, the step of our partition, and W N K is Tn K plus 1 minus Tn K. These are random values that used to define our numerical scheme. And obviously, in practice, there is no Wiener processes. This is just Gaussian and 0 delta N, independent, identically distributed. And we start exactly where our process starts, and then the scheme looks as follows. It takes what happens at the previous step and adds a linear correction. Delta N plus sigma T and K eta N K delta W and K and eta and N. It's what is our approximation of psi at time t capital. It's useful to introduce a continuous version of the scheme. It can be done in a number of ways. We consider like three versions. Only one we will use as a main version, but we will also discuss two other possibilities. A continuous version is defined as follows. So firstly, we will introduce a new function, tau n of t, which just equals t and k, when k from 0 to n minus 2, and on the last interval, t and n, which is just equal t capital, t tau n of t is just n minus 1. And this is a standard idea that what happens at the terminal time is taken to be equal to the limit from the left. So it's a standard assumption, it's a standard way to deal with it. We will not repeat, and will not care what happens at the capital. We always assume that this effectively happens. And then we will introduce a new process at n of t, which is continuous. So we start again with some interval of our partition. This is going to be equal eta and k plus a t and k, t minus t and k, plus sigma t and k, eta and k, wt minus w t and k. So this is just a continuous version of the scheme. And why we needed this function tau n, because then we can write this new process in the following form. It actually satisfies the following stochastic differential equation. Maybe not stochastic equation, it meets a stochastic differential of this form, dwt. Now, this is essentially a formal expression in the sense that from the point of view of numerical approximations, there is no way you can really model this part. You never really recover the whole trajectory of the Wiener process, but it's very useful for investigating the original scheme. And why it's useful? Because you have this differential, which provides us a possibility to use the eta formula. So typically, it's very useful in general. In what follows, we will actually avoid using eta formula, but if you want proper constants in propositions that we are going to prove, you will need it. So I will assume only linear growth condition for the first proposition, and then for any, we have this nice generalization of something that we already know effectively. That the solution of stochastic differential equation has all moments. And supremo less than t capital power scheme to the power is less than the same expression. So I will prove only the second. The first part is pretty much, it meets the same proof. So, and effectively, we will just going to repeat the idea that we used on a number of occasions already. So I gave you some type of localization. And then tau n to the power 2p. Here we are going to use two things. First is linear growth, which is a2. And the second part is that tau n of t is less than t always. So it's less than some constant. Again, it's an universal constant, the value of which can change line from line. And this is a rough estimate. And again, if you want a really good estimate, you need to go for eta formula. But I am not interested in that. This constant obviously depends on t capital. ds, so this is what we get by using that a of x to the power 2p is less than some constant, 1 plus x to the power 2p. Linear growth just taken to the power 2p. And we get here also the tau t minimum tau n sigma n tau n of s dws to the power 2p. Now, we proved that if p equals to 1, this can be estimated as a mathematical expectation of the integral from this to this over sigma squared ds. Now, one can actually prove using exactly the same method that is also true for 2p. So this integral, let me denote it e1, that e1 is actually less than some constant, mathematical space integral from tau t minimum tau n sigma 2p and s eta n tau n s ds. So 1 plus mathematical, I am adding 1 to the left and right side of what is happening on the previous line is less than some constant, say 0 to t, plus mathematical expectation integral from 0 to t, 1 plus eta n tau n of s to pds. So why I am adding 1 to make use of the Gronwon-Bellman lemma. So it's a standard trick to add 1 to, because we have 1 here. And then obviously p is less than 1 plus this. Is less than some constant, a new constant. So we did it for this situation. Now, just t to p, because we have this representation as a stochastic differential, as a sum of two different integrals, including one stochastic integral, is less than, using exactly the same tau that we just used, we obtain something like this. 1 plus which immediately gives us this estimate with a new constant. And now we can use the limit for 2 to go to the limit in the left hand side of our expression. So we started here. Here's a small correction. And ended here. So pretty much this happens. So pretty much if you have all moments of the initial solution, if it's even random, you have all moments of your... If you have all moments at the starting moment of time, the initial solution have all moments for the solution. Now, in multidimensional setting, this goes a bit more involved in terms of calculus, in the sense that you will use zeta form to the function f of x equals the norm of x to the power 2p, which is something like this, if you want a proper constant. But effectively, you could use just something simpler as Jensen inequality. So this is like dp minus 1. And you can avoid using zeta form, but zeta form, generally speaking, gives you better constants. Another interesting observation is that we used only linear growth condition. No Lipschitz continuity is required. So what we have here is can be called in terms of general ideas as a stability result. Stability result doesn't care whether you have a unique solution, etc., etc. It just says that if you give a good initial condition, you can control the propagation of this condition in this way that moments exist. And obviously this works for any type of solution. For weak solution, strong solution, doesn't care. And now we are ready to formulate our main result for the Euler-Maruyama scheme, which exactly... Now we will assume A1 and A2, and we will need both. So the first, for any p greater than 1, mathematical expectation supremum t less than t, psi of t means eta n of t to the power 2p, let's assume to the power n minus p. And we formulate the second part in the way we are going to prove it. So for any p greater than 1 and for any alpha from 0 to 1 half minus 1 over 2p, and alpha supremum of this difference, just the modulus of the difference supremum, goes to 0 when n goes to infinity almost surely. Thus, in particular, for any alpha less than 1/2 an alpha, supremum t less than t, capital psi of t and n of t goes to 0 almost surely. The third part, so in general, for any alpha greater than 1/2 and alpha limit superior when n goes to infinity and alpha, again, of this difference goes to infinity almost surely. The case alpha equals 1/2 is a bit trickier because generally speaking, n 1/2 psi of t capital, typically under rather wide set of assumptions on our coefficients, have a limiting distribution. So it falls exactly in between of these two cases. So these rates are sharp. You cannot go about 1/2, you can go 1/2, you cannot really go 1/2. And this is quite a recent result, it's like 90s. I think it's due to Proter, Kurtz, but I don't really remember. Now, This is one part of the course. We will need to use one external and very important result, which can be proved by elementary methods, but is typically a part of the martingale theory. Book holder, or Holder Davis Gandhi inequality. Let us formulate it, at least. We are not going to prove it, though, again, you can prove it using only elementary methods, but typically it's very natural to use martingale theory to prove it. It makes all arguments much more shorter and nicer. So we consider a progressively measurable process such that it has such a second moment, then for any p greater than 1, exists constant that depends only on p. That mathematical expectation of supremum of this stochastic integral to the power p after taking the modulus is less than this constant. Mathematical expectation of this integral f squared s ds, which exists, and in particular, if this exists, then we have form that might be more new constant t so this is Jensen inequality here is used. Let me clearly call it Jensen's inequality. Integral from 0 to t modulus of some function ds. Why am I writing f? Keep writing f. Q is less than t, q minus 1 for q greater than 1 even. Q ds. Q equal 1. Now, we use this a number of times in our course, and I'm repeating it here directly because I have a very strong feeling I tend to call it the Holder inequality for some unknown to me reason, but typically called Jensen's inequality. So we can estimate the supremum of this expression of the martingale in terms of its quadratic variation. For references, you can look for almost any book on martingales and / or SDs. They're going to be a proof. Now we're going to prove the main result. So the first step is a situation where we defined what we need. So this is going to be our difference. And this with star, t is going to be supremum for s less than t delta n of s modulus. Now we have delta n of t, and this is why we use this nice representation, nice continuous version of theta n. I will drop this tilde here for simplicity of the notation. ds plus integral from 0 to t a at n minus a at n. Now 1 ds plus exactly the same for the stochastic part, psi minus minus sigma of eta n dws plus integral from 0 to t sigma psi minus sigma of eta n composition tau n dws. Now, why? Obviously, if we again look at this makes no real sense in the physical world because we are not going to have a whole trajectory. So effectively, what a real world person would be interested is just a supremum of psi of t n k minus eta n k to the power to p. But it also tells us a lot about how we can recover the whole trajectory and more involved behavior of the SD. So sometimes we are not just interested in the value of some function of our solution at some terminal point of time. We also want to know whether our process hits some levels, how it behaves, how it oscillates, etc. So it tells us that the whole trajectory can be, in some sense, replicated with some error. And introducing continuous version is a very nice tool to obtain what we need. So this was a step where we did our preparations. Now using A1 and like all sorts of estimates we already know, we can get something like this. It is less than C. Let's think integral from 0 to t s to the power. This part is obvious. To EDS. So what we used here, we used exactly just putting supremum inside and Lipschitz continuity here, and Burkholder's-Davis inequality. So we replaced the supremum of stochastic integral by just the integral of the supremum. And obviously, because I using here T capital, this is how I got rid of the supremum of such expressions, because this is positive, so it just grows. So now we need to estimate this local error. Let's do it separately. S to the power 2p is less than mathematical expectation. I'm just using the definition of what eta ns is in terms of this a eta n tau essentially s to p s minus tau s to p plus ws minus w tau s. Why? Because the difference between the value of this continuous process as the continuous process stopped and the left-hand side of the corresponding interval of the partition is exactly the correction of the original scheme plus linear interpolation of this form. But now, again, using some kind of growth condition and using the previous theorem that tells us that this is well integrated and it's actually bounded, and there is no supremums inside, supremums is outside, we can effectively say this is less c. This gives us 1 over n to the power 2p, and this, by the Burkholder-Davis, just by direct calculation, gives us 1 over p. So half of this order. And this actually allows us to return here. This is now of order 1 over n to the power of p, and we just use the Groner-Balmer lemma in a standard fashion to conclude that this is less than this. Again, we do not really care about constants, so this is not an optimal constant. Now, we are going to prove second assertion of our theorem. For that, let us introduce such sets. Then by step 2, probability is less than C epsilon minus 2p and 2 alpha p. So I'm just using, my connection got unstable, but I think everything is back to normal. So this is just the Markov inequality for the moment of order 2p. And now we can check then this is less than C epsilon. Epsilon is fixed, so it just goes here. And some constant n to alpha p, and this is n minus p. And here 2 alpha p minus p is less than like p to alpha minus 1, which is less p 1 over p minus 1, which is less than minus 1. So this is a convergent series. Now, which means that by the Borel-Cantelli lemma, the easy part, the Borel-Cantelli lemma, probability an epsilon happens always from some and 0 is 1. And that's effectively what we need. Now, the fourth step, let us recall what it was. It was about proving this third assertion. And it says that for alpha greater than 1/2, we don't have convergence. We actually have this situation goes to plus infinity. To do this, we will consider a specific counterexample. So we will consider a stochastic differential equation of this form, dwt, with a specific starting condition 1. So psi of t is actually just ewt minus t over 2. Like, let's check it. Indeed, d psi of t is the first derivative of exponential dwt plus the first derivative of the exponential, which is exactly the same exponential, minus dt over 2, plus correction, 1/2, the second derivative of the exponential, which again the exponential dt. And this cancels. And this is just psi of t. Now, the Euler-Maruyama scheme, not the expectation maximization algorithm, is in this case at the nk plus at the nk sigma of eta nk, which is just nk, delta w nk. which effectively gives us a direct formula that is just 1 plus W and K and K. So we just iterate multiplication by multiplying by these expressions. And since we start at 1, so eta n0 is just 1, we obtain that our resulting approximation, which is exactly this at time 1, just a product 1 plus W and K. Now, let us assume that n0 is so large that all these are very small for all K and N. This is obviously achievable because the trajectory of linear process is continuous and uniformly continuous on compact sets for all N greater than N0. Now we can use the expansion of logarithm 1 plus x to conclude that logarithm eta n is the sum of W delta and K, which is just W1, minus 1/2 squares. So this is a product. Logarithm of product is a sum of logarithms, and we apply the expansion for every logarithm of this sum. Delta W n K squared plus 1/3. The signs are iterating. Del n K to the third power plus Rn, where the modulus of Rn is less than some constant force powers. So it is true because the reminder, if you do the decomposition of this expanding, and this is a reminder, then is actually known. Is going to be like this, dy, but now dy, because of this condition, is bounded from below. 1 over 1 plus y is bounded from above. So this is true. Now logarithm eta and n divided by psi1. Psi1 is just this, so logarithm wt minus t1 can be written. This cancels. This all is left. So I will write it 1/2 squares plus 1/3 cubes plus Rn plus 1/2 y plus, because we minus having here, with which now can be written as minus 1 over 2n sum n w squared n k minus 1 plus 1/3 sum over k of cubes plus the remainder. Now w and k is obviously just independent random variables with the known variance. So let us consider separately this part and separately this part. The mathematical expectation n1 to the power 6 is less than, here it gives us n to the power 6. And here we are going to have something like this. Mathematical expectation, the sum, n0, 1 minus 1 to the power 6 plus sum k1, k2, k1 not equal k2 I'm using the properties that such expressions are these things are independent on independent intervals. Squared, sorry, square. This is square, this is -1. And this is just to the power 4. And this is to the power 4. So we like multiply. I got rid of odd moments here in this expression. And plus some k1, k2, k3, all distinct mathematical expectation in 0, 1 squared -1 to the power. So this is what we got. And now effectively all these are just values. We don't care value of it because of the renormalization of these forms. It is just this in distribution. So effectively what affects the size of all this expression is just the number of terms. And the number of terms is the greatest number of terms is contained in this sum. So it's less than some constant n to the power -3. So there are like n cube terms. It's less than, but still. For the last two, we are going to use just force moments. And again, if you look at what happens here and you will use this normalization, this will give you -6, k1, k2, k1 not equal k2, just mathematical expectation of 0, 1. Okay. Let us do it properly. Sorry. I wanted to put. So what is mathematical to the power 4? Is mathematical expectation of the sum of cubes, delta W and K cubes to the fourth power. Now, and K is, so we get like, this is n -6 mathematical expectation, the sum of independent to the power 4. So it's less than n -6. Now, the largest number of the order of just consider what happens when we multiply k1, k2, k3, k4, psi n k1, psi n k2, psi n k3, psi n k4 mathematical expectation, but all these are identically distributed, independent, and 0, 1 to the third power. So the order of this sum can be written if all are equal is given as just n. If there is at least situation is such that k1 not equal k2, k3, or k4, this is just 0 because the third moment, not absolute moment, the third moment of Gaussian symmetrical distribution is 0, so it just disappears. So we need to get here a situation where at least we have either two pairs or we have all equal. But regardless of that, we get none greater than this amount of terms, so it's less than n to the power fourth. And the remainder in the fourth situation is actually even smaller, I think, because we have fourth terms, and here we have all sums with the number of terms not greater than n to the power 4, because we have the fourth power, so we're multiplying the sum by itself 4 times. So this is obviously just this. Now, also let us assume additionally that this holds. Obviously, if this holds for alpha greater than less than 2/3, it works for alpha greater than this, because the corresponding initial expression is going to be just bigger. And you can do this without that by considering higher orders here. So we will need the following additional claim, which is just an application, a direct application of a Borel-Cantelli lemma. If you have random variables, identically just random variables such that for some alpha there exists alpha 1 greater than 0 and alpha 2 less than 1 minus 1, and 1 is less than n alpha 2. Almost surely. This is exactly the same calculations that we did in the previous step. The series is going to be convergent, and that's effectively what you need. Thus, for alpha, which is less than 2/3, we have n alpha an1 squared, n alpha an2, and n alpha Rn all goes to 0 and goes to infinity. This is not Borel-Cantelli, this just means that it's going to be convergent. And that's all. Almost surely by this claim. So now we started that this was our A1 plus AN2 plus Rn. Now ANN, which is just ANN, eta NN, psi1 is this expression. And what I'm going to do, I'm going to multiply everything by psi1 and construct what we need. It's going to be an alpha, psi1, plus and minus 1. And by what we said, what matters when we want to consider the asymptotics of this expression when n goes to infinity almost surely is actually only the first term, because the square and already these terms are small, so you can use again some decomposition of x to the power x to obtain what you need. So let's look at it more closely. Now, this is a random variable. It doesn't matter in terms of asymptotics. It's just something is fixed for every omega. So we need to discuss this part. And this is 2 minus n, sum from k to n minus 1, and nk squared minus 1. Now, so for any k greater than 0 probability that this is bounded by this k is actually the probability that n alpha n1/2 to 1, I'm splitting this n, sum from k to n minus 1 modulus is less than k. Now, it can be written as n alpha to n1/2 times 1 over n1 squared, sum over k, psi k less than k capital, where kappas are identically distributed and independent, and it's just this random variable. But now, if you consider a sequence of such random variables, that effectively means that this convergence in distribution to some constant by the central limit theorem, which means that for any k greater than 0, there is a sequence nks such that this effectively means n to the power alpha it cannot be bounded by any constant. That's why we get here supreme. So this actually finishes our discussion of the proof of the original Euler-Maruyama scheme. Now, one can ask whether we really need this continuous version in the way that we introduced also a stochastic part to it. Maybe we can do an alternative continuous version, which eta n of t to nk plus t minus t nk. So this is just linear interpolation. And a very natural question is asked if it shares the same speed of convergence, because it's easier and more effectively natural. And actually, the answer is negative. It's worse. Because, and I told that in the previous lectures, it's hard to replicate the behavior of the Wiener process, to catch that behavior between the points we observe our situation. But I need to, let me check. So I'm 100% sure I'm writing it properly. Now, mathematical interpretation of this supremum, of this newer to the power the p, is slightly worse. We have this additional logarithm to the power p. And second part, for any alpha greater than 1/2, so while it works in mean square sense or in LP sense, it's still the same, almost surely, because this logarithm is not going to affect all the calculations we did on this last step much. We will still consider some powers of these expressions. It's pretty much would lead to the same conclusion. I'm not going to prove this result. I want just explain a bit why this is true. Because the calculations that are hidden behind this result are pretty much the same calculations that are hidden. They are very related to calculations that are hidden behind the following observations. I will just refer to Kanagawa 88 for the proof of the first assertion. The second assertion, I think it's this Faura. This is in English, this is in French, by the way. Enjoy. So I want to make the following observation because I think it's somewhat helpful. So we can define actually even a simpler version for Euler-Maruyama scheme. So instead of trying to do some interpolation, we just make it piecewise constant of this type. And this is exactly, again, the illustration that we cannot catch the behavior of the Wiener process by taking only finite number of observations. Consider now zero drift, sigma equal to 1, and then the mathematical station of supremum less than t, the n t minus psi of t squared, just mathematical supremum, mathematical station of supremum minus wt squared, which is exactly 1 over n mathematical expectation psi n k squared k 0 to n minus 1, where psi 0, psi n minus 1, identically distributed because Wiener process is stationary. It's a stationary process and independent because increments of the Wiener process are independent on disjoint intervals, and they're Gaussian. But that means that the supremum, such expression, is greater than mathematical expectation psi k, k from 0 to n minus 1 squared, which is already logarithm n to the power 1/2 squared, which is exactly logarithm n. Why? Because limit when n goes to infinity, mathematical expectation of supremums of such psi n k's divided by logarithm n squared is exactly the limit when n goes to infinity, mathematical expectation of supremums of k's without modulus, without taking absolute value, divided again by logarithm n. And I think it's this. I will give you this an exercise. This can be proven in a number of ways. It admits a totally basic, straightforward proof, but the upper limit is often proved by the means of the theory of relate by the means of the concentration inequalities in simpler cases. And actually, one can establish such types of result by using the whole phenomenon of the concentration of matter, which is quite funny. And proving that this and this have the same asymptotics is it's a nice exercise. It doesn't need much. It might need the upper bound, but it might not even need the upper bound. So I will leave this an exercise, but the calculations related to here is the calculations that somewhat related to explanation why this happens. So if you change this scheme, you lose something. Now we're going to switch to the Milstein scheme. Fortunately, we are not going to prove many things for the Milstein scheme. At least I don't think I have something really planned for it. And the reason because the calculation are not going to introduce any new ideas. They are going to be lengthy. They're going to be rather tedious. And they will need some usage, some clever usage of the Gronwall-Bellman inequality. But overall, it's pretty much the same scheme. So I just formulate the result and we will move forward, which is actually the Stratonovich integrals. So the Milstein scheme. So what is the Milstein scheme? We include an approximation of the iterated stochastic integral in the Iter-Taylor expansion. So we not only take by the way, I always considered time-independent coefficients because adding time doesn't change anything in the proof, it just makes them easier to write. Lipschitz continuity is always required uniformly with respect to the t variable with respect to space variables. And we include the approximation of those iterated stochastic integral, which is exactly this 1/2. Now, the continuous version, which is typically how it goes again for proofs. The continuous version is typically as follows on the case partition, the case segment of our partition. We take, again, I drop tilde to nk plus sigma eta nk wt minus wt nk. Now, this is a bit trickier because we will now need to write it properly. This is integral from tnk to t ws minus wtnk dws. This is one-dimensional setting. In multi-dimensional setting, you will need mixed derivatives. So this will depend on the direction, and you will have a mixed stochastic. You will have stochastic integrals with different Brownian motions. In general, this is actually kind of a problem. Sometimes people, instead of modeling iterated stochastic integrals, consider families of random variables that behave very similar in Alpecians. So instead of this, they've introduced a family of random variables that are easy to model, that are often just discrete, but they have almost the same behavior in Alpecians, where p is the order we are interested, and the remainder, the error of this approximation is lower than the whole order of the scheme. So this is how it goes in reality. Because you cannot just, well, you sometimes can, and obviously it heavily depends on what you are doing. If you're doing some toy example, or you're doing very simple calculations, you can just try to introduce internal expansion or internal interpolation for this types of integrals by adding another mesh on every step of the original mesh, etc. Again, for many problems, it's actually going to work in our modern world, where CPU time is rather cheap. It's memory that is typically expensive. So let's consider B, E. Obviously, we need higher assumption on our coefficients because we have here derivatives. This is a bit of overkill, but with bounded derivatives. Again, sometimes this boundedness can be avoided, but generally it's a standard assumption in the whole theory. Then again, for any p greater than 1, supremum over t, note that we do not push in supremum inside. This is actually important. You cannot do this. You will lose something. If not logarithm, you will lose more. And second, any alpha over p to p. Alpha supremum t goes to 0, almost sure. So the Milstein scheme is twice as accurate here, and it's effectively the same order of accuracy almost surely. However, there are some situations where these two schemes have the same order, and the Milstein scheme and the Euler-Maruyama scheme have the same order in the terms of weak error. And speaking about weak errors and all the work needed to speak about them is the last part of our course. Actually, almost all the last 5 lectures are going to be devoted to that. Now, we still have some time, so let us do some preparation to what we are going to discuss. And the reason we are going to discuss in a rather short part of the lecture is that we have a good approximation of the Brownian process. So assume that we are given Wn of processes typically of bounded variation. So we are mimic the behavior of our Brownian motion by using this like linear interpolation. So we calculate values at a fixed number, finite number of points, and we do some linear interpolations. This is going to provide functions that is very different from the Brownian motion, but still we know that Brownian motion can be constructed from such functions. There is a construction of Levy, etc., that you should be aware at this point. And so effectively, we can have the situation where they are convergent to Brownian motion in, for instance, subnorm. This is one of the way to actually build a Brownian motion. And they can actually solve kind of stochastic differential equation, but with respect to these processes. As we will discuss, they're actually well defined. Wnt dt. This is now not a stochastic Ito integrals, it's just a random Lebesgue-Stieltjes integral, because this is of bounded variation. And the natural question is, what is the limit of Xn? Can it be that we can just model the solution of the Brownian motion by using this approach? Because it seems an alternative to the whole setting we just discussed. We started with modeling the whole solution. But now one can ask, maybe we can just model in some way the Brownian motion, do this, and then we almost get our solution. And the answer is actually negative. The answer is negative. You don't obtain this. You obtain something corrected. And to do this, we will need to discuss something what is called the Stratonovich, sometimes called the Stratonovich-Fisk stochastic integral. It's going to be a very short. I'm not going to prove much. But the idea. So recall that for any alpha from 0 to 1, again, t and k is going to be k divided by n times t. K lives from 0 to n. N is a natural number. We discussed that was an exercise in our course, but it's not a hard exercise, actually. It's a rather simple exercise. That you can do something like this. You can consider averaging between times on the case part of the segment of your partition. Consider W and K. And this is going to converge in even L2 to 1/2 W squared T plus 2 alpha minus 1 pk. So if alpha equal if alpha equals to 0, we just recover the original eta integral. If alpha is different, or alpha is equal to 1, we will recover so-called backward eta integral. But if alpha equals to 1/2, we obtain the idea that instead of using W, delta, and K in our simple integrals, we can actually consider a different approximation. This still is going to be well-defined for obvious reasons. But this leads, even in the simplification, to the expression this is different from the eta case. Now, here, instead of this, you can actually do the following. Instead of considering different types of averaging inside, you can do this. This is sometimes it's even better because you have two observations of your Brownian motion. You interpolate differently to the eta case. And one can actually repeat the eta theory, but instead of using this as integrals for simple processes, one can do something like this. And this is going to result in a different limit. However, it's easier to introduce this expression by using the eta integral already. So we consider a progressive process that admits such representation as the sum of two integrals. So here A, sigma are progressive. And I will also require that they have proper second moments, which is typically overkill in the situation, but still. And then one can prove the following interesting theorem. So for function that is slightly better, so It's slightly better than what happens in the situation of Ito integral. For Ito integral, we discussed similar sums, and f was just a process that was continuous. It was sufficient for us. It required that this expression was continuous in square mean. We had a proper statement. You can check. Now, this convergence probability, we don't need much, but you know, two effectively. Psi of S, dws. This is the eta part. This what would happen with just takes here psi t and k, no 1/2 here and no this term, plus a correction. Why am I writing f prime psi of s sigma s ds. Now this expression is often denoted as f psi s dws, the Stratonovich integral of phi psi with respect to w. So this is the definition of this expression. Again, you can start by this and prove this, or you can like do this exploitation of the existence theory. Note that f is better. In the Ito case, we consider very different kinds and types of integrands. Here we are restricted to rather good functions. It actually simplifies the life a lot. Because if you're going to speak about some limits of such expressions and you have some assumption on how good this function f is, it takes a lot of problems away, because in what we did previously in our course, we considered very general integrands. We proved that they can be approximated, that the corresponding sums are convergent. But here, this condition enables typically to use something like, let's Taylor formula simply. Let's assume also additionally that the derivative is bounded. So I am going to just explain the situation informally. So I will use the Taylor formula, like literally the Taylor formula, almost surely. This is, this equals like f psi t n k plus 1/2 psi t n k plus 1 minus psi t n k. Now, then this equal f psi t n k plus 1/2 f squared at some point t n k. This between psi t n k and 1/2 psi t n k plus psi t n k plus 1. And here we have our shift. That means that we have now considered the sum by adding multiplication. So we have f 1/2 plus 1/2 delta w and k. This is f psi t and k delta w and k plus 1/2 f squared t and k. We even discussed that you can work with measurability of such expressions, but actually theta and k is also measurable. We also discussed that. And here I'm going to write integral from t n k plus a psi of r dr times delta w and k plus 1/2 f squared theta and k, f prime, t and k plus 1 sigma psi of r dwr and k. Now, this should lead, when we consider the sum and the limit, to just integral psi of s dws. Now, these two parts are treated differently. Let's consider a1 and n2. So if we think about k, I and 1k. So what is going to be the limit of this expression? This is something bounded, this is constant. This has, roughly speaking, order delta t and k to the power of a square root in terms of square mean. But this is delta t and k, just. So this is like the sum delta t and k to the power 3/2. So this should go to 0 and shouldn't influence the limit. This is the idea, effectively. So this is of, like, this term is of order 1 over n to the power 3/2. And if you consider the second term, again, this is something that should be convergent. This is 1/2. This is again of order 1 over n to the power 1/2. But this is a stochastic integral. This is of order 1 over 1/2. So this should contribute to the limit. And this indeed contributes to 1/2 integral from 0 to t capital f prime psi of s sigma psi of r. But now, since we have like delta w and k squared, this should give us the ordinary integral. So this is the intuition that can be made formal. Why we have this correction? And this is exactly the correction in Stratonovich integral. So again, let us repeat that integral from 0 to t f psi of s, only for rather good f, this is defined. It can be done in general situations, rather general situations, but it's actually not easy. This is by definition integral f psi of s, the ordinary integral plus correction, 1/2 integral from 0 to t f prime psi of s sigma psi of s sigma ds. Effectively, sigma just depends on s. So here should be sigma of r, just, and sigma of r. And effectively, one can actually define, again, by definition, this is. Now, one can say that we considered a very specific definition of Stratonovich integral, but sometimes in literature you can see a different definition. So instead of averaging between points, we take a value of psi at an average of the interval. And next time we will speak what is the result of such expressions. This will, under very wide set of assumptions, lead to exactly the same situation. So you can define the Stratonovich integral in two different ways. But overall, this is a more general case. Okay, does anyone have any questions? Good. Then see you next time and good luck.
Thank you. Bye.
You're welcome.